Section 6.9, using applying hyperbolic functions to velocity. This example here, we have an ocean wave, and we have a formula for the velocity. V is equal to g times L over 2 pi times the hyperbolic tangent. V is equal to square root of g times L over 2 pi times the hyperbolic tangent of 2 pi d over L. So g is the acceleration due to gravity, 32 feet per second per second. L is the length of the wave. On this example, it's 4 pi feet. And d is the depth of the water. In this case, we're saying it's 16 feet deep. So we can plug into that formula to get the velocity of the wave. That's going to be v is equal to square root of 32. V is 32 times 4 pi over 2 pi, and hyperbolic tangent of 2 pi times 16 over 4 pi. Okay, so the pi's will cancel. And we'll get 32 times 4 is 128, divided by 2 is 64, so it's square root of 64 hyperbolic tangent of 2 times 16 is 32, divided by 4 is 8, hyperbolic tangent of 8. So this square root of 64 is 8, so this is going to be 8 square root of the hyperbolic tangent of 8. And this is pretty close to 8. It's 8 square root of e to the 8 minus e to the minus 8 over e to the 8 plus e to the minus 8. But e to the minus 8 is going to be pretty small. So basically, this is pretty close to e to the 8th divided by e to the 8th, which is pretty close to 1. So it'll be 7.999 and very close to 1. So you can put it in a calculator and compute, but approximately 8 feet per second. The velocity of the wave. Okay, so another application would be the velocity of a falling person through air. If there's no air resistance, then it's just governed by the acceleration due to gravity. But if there's air resistance, then it's going to be a more complicated formula here. And we have the formula of v of t, velocity at time t, square root of mg over k times the hyperbolic tangent of t times the square root of gk over m. So m is the mass of the person falling. In this case, we'll say it's 40 kilograms. G is acceleration due to gravity, 9.8 meters per second, at least near the surface of the Earth. K, we're going to use 0.5 kilogram per second for the air resistance. That's K. And then so if we plug into the formula, after 5 seconds, we're going to get, let's see, v of 5 is going to be square root, just plugging in the numbers, 40 times 9.8 over 0.5 times hyperbolic tangent of 5 times square root 9.8 times 0.5 over 40. Okay, so actually this square root does not go all the way across. Okay, so the first square root, 40 times 9.8 over 0.5, that comes out to be 28. And we'll have the hyperbolic tangent of 5, and the second square rooted expression comes out to be 0.35. So it's going to be 28 hyperbolic tangent of 1.75. So it's 28. And the formula for hyperbolic tangent is e to the 1.75 minus e to the minus 1.75 over e to the 1.75 plus e to the minus 1.75. And if you put that into the calculator, it comes out to be about 13.6 meters per second. Okay, okay, so velocity after 10 seconds. Up to this step it's the same, except instead of a 5 we'll have a 10 here. 10 times 0.35 is 3.5, so we're going to have 28 hyperbolic tangent of 3.5. So that's 28 times e to the 3.5 minus e to the minus 3.5 over e to the 3.5 plus e to the minus 3.5, and that comes out to be 27.9 meters per second. So so the velocity has increased from 13 meters per second at the 5-second period to 27.9 meters per second. And then for the terminal velocity, we take the limit. This is the, instead of a 5 here, this is the same formula we have up there, but we just leave the letter t for the time. We take the limit as t goes to infinity. So it's the limit as t goes to infinity of 28 e to the 0.35 t minus e to the minus 0.35 t over e to the 0.35 t plus e to the minus 0.35 t. And as t goes to infinity, these it's going to be denominated by these two terms here. It's going to be which go to 1. It's be very close to 1. So this is going to be at 28. So it's going to go to if you multiply top and bottom by e to the minus 0.35 t. I'm running out of room, but it's supposed to be 0.35 t here. You'll get the limit as t goes to infinity of 1 minus e to the 28 times 1 minus e to the minus 0.7 t over 1 plus e to the minus 0.7 t. So the limit will go to 28 times 1 minus 0 over 1 plus 0, which is equal to 28. So the terminal velocity is 28. So if there were no air resistance, the person would keep continue to accelerate until they hit the ground. But with the air resistance, eventually there's air resistance actually balances out the acceleration due to gravity, so the person doesn't go any faster. Okay, so okay, we can also compute the acceleration by taking the derivative. So we're going to use the formula for that particular person falling, the 40 kilogram person. For that person, the velocity is 28 times the hyperbolic tangent of 0.35 t, and we can use that to find the acceleration at a given point in time. So a of t acceleration is v prime of t. And so we have a composite function here. The outside function is a hyperbolic tangent. The inside function is 0.35 times t, so we use a chain rule. The 28 is a constant. We just copy the 28. That's going to be a constant. The derivative of a hyperbolic tangent is hyperbolic secant squared of 0.35t, and the derivative of 0.35t is 0.35. So it's and then if you multiply 0.35 times 28, you get 9.8 such squared of 0.35t. So acceleration at time 0, a of 0 is 9.8 such squared of 0, and so that's 9.8 times 2 over e to the 0 plus e to the minus 0. And it's going to be 2 over 1 plus 1 times 9.8 is 9.8 meters per second. Okay. Acceleration at time 5, a of 5, 9.8 such squared of 5, and it's going to be 9.8 times 2 over e to the 5 plus e to the minus 5, and you can put that in the calculator. It's actually it's going to be 1.75, 9.8, 5. This is 5 times 0.35. So it's such squared of 1.75, and it's 9.8 times 2 over e to the 1.75 plus e to the minus 1.75. And again, you can put this in the calculator. It comes out approximately 1.1 meters per second. And then a of 10, acceleration after 10 seconds, 9.8 such squared of 10 times 0.35. That's 9.8 times. This is squared. This is squared too, but it doesn't matter. Okay, so this is 9.8 times 2 over e to the 3.5 plus e to the minus 3.5, and that's squared. And that comes out to be about 0.04 meters per second. Okay, so and then the terminal acceleration, we want to take the limit. So the limit as t goes to 0 of 9.8, and this is going to be 2 over e to the 0.35t plus e to the minus 0.35t. And the denominator goes is going to, and this is squared. So the denominator is going to become large, and that means this is going to go to 0. So the terminal acceleration is going to be 0 meters per second. Okay. So the at that point the eventually the air resistance completely balances out the acceleration due to gravity. Okay, so we can also integrate v of t to get the formula for the distance. So again, v of t is 28 times the hyperbolic tangent of 0.35t. So if we take the integral v of t dt, integral 28, and we could write this as the sinh over the cosh, sinh of 0.35t over the cosh of 0.35t dt, and let's let u equal cosh of 0.35t, and then du is going to be sinh of 0.35t times, this is a composite function, so times the derivative of the inside, it would be times 0.35 and then dt. And then, so if we solve for dt, that means dt is going to be 1 divided by sinh of 0.35t times 0.35, and then this times du. Okay, so so if we take the antiderivative, this is equal to the integral from 28, and I want to place well, copy the sinh 0.35t. Replace the denominator with u. U is equal to cosh of 0.35t, and I'll replace dt with this expression here. This is 1 over sinh 0.35t and 0.35 du. So 28 divided by 0.35 is 80. So we go 80, and the sinh is going to cancel. So we'll have 80 times 1 over u du, which is equal to 80 ln, absolute value of u, plus a constant, and then we could back substitute. U is cosh of 0.35t, so this is ln cosh 0.35t plus a constant. So if we evaluate this from 0 to some particular time t, so the we take the definite integral 0 to t of v of t dt, we're going to get 80 ln cosh 0.35t, and we don't need the constant for the definite integral. We don't need the plus constant. We just evaluate this from 0 to t. At 0, cosh 0 is 1, ln 1 is 0, so the bottom limit drops out, and we just have the top limit of 80 ln cosh of 0.35 t. So if we want to find the distance after 10 seconds, so this part here, d of 10, is the distance after 10 seconds is going to be 80 ln cosh of 10 times 0.35, it would be 3.5. So it's 80 ln of e to the 3.5 minus e to the minus 3.5 over 2, and you can put that in the calculator. It's approximately 225 meters. Okay. So those are a couple of applications of hyperbolic functions, and that concludes this presentation.